I'd like to start this lecture with what I'd intended to be the second half of Monday's lecture. So on Monday, we started talking about frameworks in 2 dimensions that were nearly but not quite generic. And so if you remember, we talked a lot about frameworks with 2 coincident points and showed that already that special case was enough for there to be both quite interesting theory needed, and it was applicable to certain situations. As a similar setup happens if you talk about frameworks of collinear points. So of course, any 2 points define a line, but if we have at least 3 points that are collinear, then you're definitely not a generic framework. And so that's what I want to talk about for the first half of this lecture. Okay, so what are we going to say? We're going to take a graph G and we're going to pick 3 special vertices, X, Y, Z in the vertex set. And I'm going to take a minimally rigid generic realization of the graph in R2. So suppose I've picked a graph which has such a property. So I've picked a minimally rigid generic graph. And the question is, for these 3 special vertices I've picked, when does there exist a framework of the graph such that everything is generic except Px, Py, and Pz are collinear, and the resulting framework has to be minimally rigid still? So when can I realize 3 points in a collinear way without destroying the rigidity? Okay, so a very simple example would be to take the complete graph on 3 vertices. It should be clear that when we had this before, when we talked about collinear triangle for the 1 extension technique, that this is not infinitesimally rigid. So I'm always going to be talking about infinitesimal rigidity when I have my non-generic realizations. And we saw that the 3 rows in the rigidity matrix are dependent if the 3 vertices of a triangle are collinear. Okay, so this is obviously one very small example, but it really does model what happens in the general situation. So if we have a general minimally rigid graph and we have set 3 of the points to be collinear, what can go wrong? Well, it's really just generalizations of this picture. So for example, let's replace the edge between vertex X and vertex Y with a bigger critical set. So remember, a critical set is a subset of the vertex set X such that the number of edges induced by X is 2x minus 3. And a single edge has 2 times 2 minus 3 is 1. It is an example of such a critical set. But if we replace xy with a larger critical set Z, which contains x and y, it contains the 2 ends of the edge xy, but it does not contain the 3rd vertex, then it may be that we've just picked a critical set which contains the edge xy, and then we haven't really changed the example of the dependence, but it may be that it doesn't. And so it may be that we have a picture like this one where I've picked some minimally rigid generic framework, which includes the vertices x and y, but does not include z. And because it's rigid, the length of xy is determined. So in language of the rigidity matrix, the row that you would write for the edge between xy is some linear combination of the rows for these 5 edges. And so the edge is in effect implied, and so the dependence that you get from the collinear triangle extends to this situation. And of course, when you see you can do that, you could also do the same thing to the other edges in your collinear triangle as well. So what you can think of as the collinear triangle problem, the triangle being dependent with the 3 vertices collinear extends to a general picture like this. So you have 3 critical sets, an x, a y, and a z, which each contain 2 of them. The intersections are exactly the 3 single vertices x, y, and z. Whether any of the sets contain the particular edges xy, yz, or xz or not, this will still have the same dependence from this now completely implied triangle. Okay, so let's say a structure like this one is an obstacle for the special triple. Okay, so it's a set xyz of critical sets where each of each pair intersecting the relevant vertex, and this is going to be the only reason why a framework with 3 collinear points that was minimally rigid suddenly becomes not rigid infinitesimally with the realization of those 3 points collinear. Okay. So we already talked about such critical sets before, and so we saw earlier in the course that if you have an obstacle x, y, z like this, then the union is critical and there are no edges between them. So in this picture, there were no edges like this, this, or this. Okay, so here's the theorem. And so these obstacles were introduced by Jackson and Jordan in 2005, and they studied this problem with the collinear triple x, y, and z. So I take a minimally rigid graph in the plane, and then I want to know, does there exist some realization which has the property that px, py, and pz are collinear and is infinitesimally rigid? And the answer is, so you take your 2-3 type graph, your minimally rigid graph in the plane, and as long as it contains no obstacle, as I've just described. So this is a very concrete description of exactly when this collinear realization fails to be infinitesimally rigid. Okay, so I decided not to go into the details of the proof. So I'll just make one small remark, is that it would have been a natural thing to include in the course because it's the same proof technique that we've used a lot. So it's based on the fact that 0 and 1 extensions preserve rigidity, and the difficulty and what takes quite a while in their paper is to deal with the 1 reductions and avoid creating these obstacles. So as you're doing your 1 reductions, as well as checking the 2-3 sparsity condition, you also need to avoid creating new obstacles for your triple. Okay. The next thing I want to do is extend this result from a collinear triple to an arbitrary subset of the vertex set that's collinear, and allow, so I can have an arbitrarily sized subset of the vertices that are collinear, and that the cost will be that this condition on when it's minimally rigid will become much more complicated. Okay. So what's the idea? Well, I'm actually going to say almost nothing combinatorial. I say the combinatorial characterization would be much more difficult, but what I'm really going to do is avoid combinatorics by relying on a previously known combinatorial result, which I'll mention maybe in about 10 minutes, and instead just use a geometric transfer, a projective geometric transfer of rigidity, which goes back to what we talked about a number of lectures ago. So a while ago, I introduced frameworks on a sphere, and I showed you, so by hand, these row and column operations, which transferred infinitesimal rigidity from the unit D sphere to the plane, say z equals 1, the last coordinate equals to 1. And what we were really doing was we had a picture like this one, where we had a point on the sphere, and we used the unique line defined by that point and the center of the sphere, and we were able to slide that vertex by these row and column operations to the plane at z equals 1, say we're on the 2 sphere, just for simplicity of the explanation. And the thing that we talked a little bit about there, I think it was pointed out as a comment, and I explained a little bit there, was that this transfer becomes a little bit problematic if you have points on the equator of the sphere, because instead of being moved up to the plane, they say here heads off to infinity, and so you have to move to sort of a projective view and include what happens when there are points on the equator. So before I move on in the words, let me just show. So here I've got 3 points on the equator, and the same thing happens as a collinear triangle if you're thinking about a framework on the sphere, that if you have these 2 edges, then the other one will be dependent. If you think about that as Euclidean distance edges, and this is completely clear because it's the same as in 3-dimensional space, where a completely flat collinear triangle would be dependent. And if you think about it on the sphere with geodesic edges, it's that when you go around the other way, any two of the three edges determines the third distance still. But what I also wanted to show you with this picture, just before I move on, is that I have these 3 points on the equator. What I want to do is apply a rotation of the sphere, and that rotation would just be a very small rotation, so any other point doesn't end up accidentally going back to being collinear, but these 3 points will rotate off the equator to some other great circle. So there'll be some great circle somewhere. The picture was not very good, but now they're all not on the equator. I can invert any point that was on the lower hemisphere up to the upper hemisphere, and then I can send them all off to the plane. The cost being that the points on the same great circle will be collinear up in the plane. It won't look like the line I've just drawn, but the points that are on the same great circle of the sphere will end up collinear in the plane. And hence, if we can understand frameworks on the sphere with points on the equator, we can transfer it via the same row and column operations, dealing with infinity, which is a little bit more complicated, but I'm going to omit that challenge, up to the plane and say that the infinitesimal rigidity of the object up here with some subset of points collinear is equivalent to the infinitesimal rigidity down here with that same subset of points lying on a great circle. Okay, so let's see some of the words to explain that. Okay, yeah, so this is what I was just explaining. So very roughly, you have your points that lie on the unit. Let's always talk about two spheres in R3. So it lies on the unit 2 sphere, and say some subset of points lies on the equator, then we assume everything else is sufficiently generic that a small enough rotation won't move any other point onto the equator. And so a small rotation, which of course preserves rigidity of the whole framework, moves it so that no point lies on the equator anymore. And now we can apply the same row and column operations as we used to apply to move the framework to the plane, except the cost is that the plane framework won't be generic. It will have some subset of points that are collinear. Okay, so this is a very rough explanation of the following theorem, which a sort of key part of this theorem I'm going to explain after the statement as well. And again, it will only be sort of hand wavy. So I need to introduce some notation to describe the combinatorial condition, which you'll see is significantly harder than the usual count conditions that we've had. So give a graph and a specified subset of vertices x, and x is going to be the subset of vertices that are going to be on the equator of the sphere or will be realized collinearly in the plane. So for a subset of the edge set of the graph, for a subset A, I'm going to use V sub x of A to denote the number of vertices in X which are incident to edges in A. Okay, so that's going to come up in our combinatorial. So the theorem is just too big to fit on the page, so let me just shrink slightly. Okay, it wants to shrink a lot. Okay, so this is a theorem due to Yasser F. Tekhari and a group of us whose names are probably familiar to you. What we do is we have a graph and we take a subset of the vertex set. Then we say there exists an infinitesimally rigid framework GP in R2 such that the points assigned to X lie on a line. So you can imagine everything else is generic. The points in X are generic along some line, and that they're allowed to move off the line. They just happen to lie on that line in this realization, and it's infinitesimally rigid. If and only if, when your graph contains a spanning subgraph G dash, so it's a spanning subgraph, it's the same vertex set, possibly a subset of the edge set, possibly the whole thing, with 2v minus 3 edges, which is the natural Lemang count. We still have to be, just like in the Jackson-Jordan case, we still have to have a 2-3 tight graph, but we have a more complicated subgraph condition that not all 2-3 tight graphs satisfy. So we have to be a bit more careful. And to see examples that don't satisfy it, you can just look at the free collinear point case where you saw, and you can imagine that for sure you get similar obstacles for quadruples and 5 tuples, etc., by making very flat. So any collinear cycle will be dependent. So you can make yourself many examples using that. So what's the subgraph condition? So you take any subset of the edge set of this spanning subgraph, and you take any partition, A1 up to AS, of the set of edges you've picked in E prime. And then what you need to be true is that the size of the set of edges you picked A is at most this sum. So you want to go through each element of your partition. You look at A1 up to AS, and you take this V sub V not X and V sub X of the two things, and you have the Vx twice, actually. So you have Vx for the whole thing. And I guess I don't want to spend any time going into the details of why this is quite the right combinatorial count. The one thing I'll try and say to give you a sort of flavor of it is that in some sense what we're doing is we're taking the cycle matroid. So we're having the mod V minus 1 matroid, and we're having the mod V minus 2 matroid, 2 mod V minus 2 matroid. And we're taking a matroid union, but there's also a sort of an operation called a Dilworth truncation going on here. And so I haven't defined matroid union or Dilworth truncation in the course. So in some sense, there are two nice and easy to understand count matroids, but then there are more complicated operations going on, which leads to this precise, but a bit complicated to understand and digest, at least at first viewing.
Tony, sorry, it's Will. Could I just ask a quick question? What is the Vx, V sub X here?
This was
sorry, I missed that.
So it's here. So let me say it again.
I see. I missed it up here. That's why.
So you take a subset of the vertex set and a subset of the edge set, and then V sub X of A for the relevant subsets is the number of vertices in X which are incident to edges in A.
Thanks. Okay. Okay,
but I don't want to dwell too much on this. I don't think I understand this combinatorial condition in a great amount of detail, so I don't want to dwell too much on it.
Could I actually ask one other question? I understand, I guess, what the proof is, or what the theorem is saying, but I was expecting things to go in a slightly different direction. So if you have like this takes 3 collinear kind of points and extends to 4 or 5 or more collinear points. What about the situation where you have 3 collinear points and then a different set of 3 collinear points? This
is a very interesting question, and I think people are looking at this. I thought about it a little bit myself, and I just don't have don't know what that is. I don't know a really good way to go about it. So you're completely right. It would be interesting to take sets X, Y, Z, I should have used X1 up to XK or something, where there is lots of different lines, and there happens to be, say, 3 points on this line, 3 points on this line, 3 points on this line, and do that. And if the number of lines up here is sufficiently small, then it may be possible to extend the Jackson-Jordan theorem in this kind of direction, because you'd want no obstacle for the triples on each line, and then you'd have to worry about how the lines interact with each other. But their proof actually combinatorially was, well, it was an entire journal article, the paper. It was maybe 15 pages of combinatorics. So it's not going to be a trivial extension, and 3 points on a line is maybe not quite what you want. You'd want each of these lines to have lots and lots of points. And so what would be nicer, I think, is if this kind of combinatorics could be extended, but I have no idea how to do that. So the proof here is really from the projective context and there's only one line at infinity that we can use. So I really don't know how to get a second line in the techniques we were talking about. So as I say, I think some people are working on this. So I hope there are some nice results in the near future, but
that's an interesting point. Okay, interesting.
Yes, so let me go to here. So I wanted to, basically in this theorem, in some sense, this theorem you can think of as a corollary to another result. So what I explained was why frameworks in the plane with collinear points was equivalent to frameworks on the sphere with collinear points. And that was via thinking of them as frameworks with including points at infinity. You can also translate that to another problem, which we could show was equivalent by the same kind of row and column operations, which is to the study of point line frameworks. And in fact, we could do this in d dimensions. So it could have been, this could have been RD, and this could have been the D sphere, and then there would be point hyperplane frameworks. And the actual theorem I quoted is really saying, really what happens is that this rigidity condition is equivalent to the point line condition. I'll tell you what point line means in a minute, to a point line rigidity condition. And there was a pre-existing theorem that point line rigidity was equivalent to this combinatorial situation. So in some sense, our paper, we didn't do anything combinatorial for this result here. It was the projective geometric transfer and then applied a previous result. We did other combinatorial things in the paper, but at this point we didn't. So what are the point line frameworks we relied on? So again, I'm going to be very brief. And in fact, what you can see is basically all I'm going to say. So I take a graph and I'm going to partition both my vertex set and my edge set. So the partition is going to be into VP and VL, where I think of this is point vertices and this is line vertices in my point line. Well, a graph at this stage, but it's going to be a point line framework in a moment. And my edges are going to be partitioned into point edges, point line edges, and line edges. Okay, and so then a point line framework is a pair which realizes the point vertices as points and the line vertices as lines, and each edge corresponds to the relevant thing. So an edge in EPP gives me a point-point distance constraint, so that's our usual constraints between points. An edge in PL gives me a point line distance constraint, and an edge in ELL gives me a line angle constraint. So you could imagine a graph like this one where the partition of the vertices is into filled and unfilled circles. So the filled circles are the points, so they just get realized as points, and the unfilled vertices are the lines, so they get realized as lines. And then in this picture, there's no edge between the two lines, so there was no angle constraint between the lines, but there is an edge between the 2 points, so there's a distance constraint between points, and the rest are sort of point line distance constraints. And so you can ask about the rigidity of such a system. So your lines are allowed to translate and they're allowed to rotate, and your points are allowed to move freely subject to the constraints. And so one thing beyond the usual 2v minus 3 condition, and I mentioned this before with the cycle condition, is that if you have a cycle of angle constraints, then the last one is always determined. So you need to be a forest on the line. So the ELL should be at most VL for any subset of your graph on the lines. And so this gives you a second count to incorporate with the usual one. And this is where some of the complication comes from, at least. But there is a nice paper, and I should have referenced it here, so sorry about that. The paper is by Bill Jackson and John Owen, where they prove, I've forgotten the year, I'm sorry, but they prove that a point line framework is rigid if and only if the combinatorial condition up here, which I'm in danger of having far too much color all over this bit, but this combinatorial condition is equivalent to rigidity of a point line framework. And so the theorem stating here was really saying that this collinear condition is equivalent to rigidity is equivalent to point line rigidity. Okay, so that's the end of what I wanted to explain last time. I've now caught up. Are there any questions on that before I move to a different OneNote file? Yes, this is the right one. So I'm going to change topic basically completely to something called Azure Decompositions. So actually, this was something I was and ahhing about including, but Sean, who I can see is here, said he did want to hear a bit about them. So let's see what I can say in the second half of the lecture. So what's the idea? So the idea is motivated by engineering. So in fact, there was an engineer maybe 100 years ago called Leonard Azure, who, and in the engineering community, sometimes what I'm going to call Azure graphs are known as Azure groups. So they're not groups, they're graphs. So we have to go to graphs. The idea is if you want to control some mechanism, then a nice thing to do is to break it up into easier parts. So you take, let's say we're in the plane and we have something that's minimally rigid. If we delete any one edge, we'll create a mechanism. We'll create a motion that they might want in some mechanical engineering piece of machinery, say. And what the Azure idea is to break your minimally rigid thing up into the smallest parts. So when you remove an edge, you know exactly how it's going to move. So we will look at minimally rigid objects and look at what rigid subgraphs are inside a minimally rigid graph, except we're not going to do it for arbitrary minimally rigid graphs. We're going to do it for pinned graphs and pinned frameworks. So I could use the language we had of linearly constrained frameworks from earlier, but that's not consistent with the literature on Azure graphs and Azure decompositions in rigidity. So I'm going to move the notation a little bit. So I'm going to partition my vertex set, but this time I'm going to partition the vertex set into I and P. So I'm not so keen on this notation, but this is what was used in the literature. So I means inner and P means pinned, and you still have your edge set. So our vertices some of them will be pinned, which means that any infinitesimal motion at that vertex must be the zero motion. It doesn't move in any continuous motion. And inner vertices are ones that are allowed to move freely. So unlike linearly constrained frameworks, we don't have the option in the middle where there are, say, sliding constraints to fixed hyperplanes or just fixed lines in the plane. Okay, so a pinned framework, well, it's just a pair GP, so we just have a map which assigns positions in D space to the inner vertices and to the pinned vertices. And we can do a pinned rigidity matrix. So again, this is distinct from linearly constrained, but equivalent, because what we're going to do to pin the vertices, we're going to insist that the infinitesimal motion of those vertices is zero, which we achieve by striking out the columns. So there are only columns of the rigidity matrix, the pinned rigidity matrix, for the inner vertices. Any pinned vertex has its columns thrown away. Okay? So because we've thrown away the columns, we can throw away isometries because these vertices become pinned, so we can't translate or rotate if we have enough of these pinned vertices. So what we're going to say is that the framework is pinned D-rigid, so it's in dimension D, if the only infinitesimal motion is actually just zero, so assign velocity zero to every vertex. And so because I've thrown away the columns for the pinned vertices, I only have columns for the inner vertices. I have D of those since we're in dimension D, and I've got rid of all isometries. So I've got rid of everything in the kernel. So the rigidity condition infinitesimally is equivalent to the rank of this pinned rigidity matrix being equal to the number of columns, which is d times the number of inner vertices. And so we have pin D rigid, we can have pin D independent if the rows are linearly independent, and pinned minimally D rigid if it's pin D independent and also pin D rigid. So this is just exactly as usual. And we can define, because I want to talk about generic frameworks, I have to be a little bit careful because I'm going to allow the pinned vertices to not necessarily be generic. That's not required as long as they aren't all coincident. But the inner vertices will have to be generic. But I can talk about these rigidity concepts for the graphs as well as for the frameworks, because I'm only interested in the generic situation. Okay, so remember, for the linearly constrained world, we talked about and proved a theorem of Strano and Ferran, which included the case, so linear constraints include the case where there are multiple linear constraints at a vertex. So you can have, say, two in the plane that the two lines are not parallel. So they restrict a vertex to a set location, the intersection, and hence that's a pinned vertex. But the theorem just for pinned frameworks was proved a little bit earlier by Brigitte Servatius, Offa Shai, and Walter Whiteley. So what does it say? Here it is. I'm not going to prove it. We proved the slightly more general one, so I don't think we need to prove this one. It can be proved. In fact, I think that they did prove it via 0 and 1 extensions. So I take my inner and pinned vertex set, and I set the locations of the inner vertices to be generic, and the locations of the pinned vertices can't all be the same place, so it spans at least 2 distinct locations. Then the framework GP is pinned minimally 2 rigid, so this is a generalization of Lemann's theorem to include pinned vertices, if and only if the number of edges is equal to twice the number of inner vertices. So it doesn't matter how many pinned vertices you have, as long as you have at least 2 distinct locations. The count is just in terms of inner vertices. But for subgraphs, we have to care about the pins a little bit, but not too much. So for all subgraphs G dash, I dash union P dash E dash, we have the standard inequality that compares to this one everywhere, but in particular, we care when that's at least 2 pinned vertices in the subgraph. When there's only exactly one pinned vertex in the subgraph, we have a slightly stronger inequality. And when there's no pinned vertices in the subgraph, and there's at least one edge, then we have the standard Lemann inequality. So we have an even stronger inequality. We need to be true. So I think this situation should be relatively clear. So if you had this one, so say I have 2 pinned vertices like this and 2 edges like that, and then the 4 vertices up here in the K4 are all inner vertices, then this graph has 8 edges and 4 vertices. So E equals 2I happens. This inequality is always satisfied, but what goes wrong is that if we have no pinned vertices and you just look at, say, this subgraph, we fail the Lemann condition. So it should be relatively clear you need this. And if you think for a moment, you also need this one as well. And then they turn out to be the natural answer to give exactly this pinned minimal 2 rigidity. So as I say, this is a special case of a linearly constrained result. We did go through the statement in proof out, but we used a different language there with looped simple graphs, whereas here we're using this inner and pinned. So I wanted to dwell on this statement a little bit. Any questions?
Yeah, so the generic condition is only required for the inner vertices in this. There's no assumption on the pinned vertices.
As long as it's not all the same, if all the pinned vertices were in the same place, you'd still be able to rotate everything around that center. But as long as there's 2 distinct locations, it's okay.
What if I was to do a pinned vertex in the position of one of the inner vertices? So I create like a 0 length edge. Is that also allowed or not allowed?
Okay, yeah, you're right. So we're not allowed to have 0 length edges. So you could have it that, so say this wasn't a complete graph here, I could have this pinned vertex could overlap with, let's say I just had a zero extension on here. So this pinned vertex could overlap with this one because its edge would still be fine. But as you say, if you put a pinned vertex on top of an inner vertex that's adjacent, the row in the rigidity matrix would be the zero row. So yes, you're right. Actually, I thought I copied the theorem statement from their paper. So I wonder if maybe they made an assumption that there was no coincident points earlier on, but as you say, it will create a zero row, right? So it must be excluded.
I think there must be other generic conditions, because you could have a pinned vertex, the rest of the framework somewhere, an inner vertex, and you could have the inner vertex forming a line or something like this, and then you would have a problem.
I've got a pinned. Say again. I've got a pinned vertex.
You've got a pinned vertex, you've got an inner vertex connected to the pinned vertex, and one other vertex which causes a collinear triple, so one other inner vertex or something like this.
Yeah.
Then this is a problem, right? Because you still got an infinitesimal flex.
So say this was pinned.
Yeah.
Then this is still minimally rigid. This is still the rigidity matrix here would have rank 2. Say we're in the plane.
Okay. But it should have.
And you're not allowed edges between pinned vertices. I don't think I said that, but that should be relatively clear that.
Yeah. Okay. Yeah.
They're both pinned, so this is this one would obviously be dependent.
Yeah. But I don't think that's infinitesimal. I don't think that's minimally rigid though, because you can put a flex coming out of the middle vertex that's orthogonal to the two edges connected to it, right? So there must be something in the kernel of the rigidity matrix.
Oh, that's true.
I think there needs to be some sort of like the.
Oh yeah, you're right. Of course, aren't you? Because I mean, these ones are struck off.
I think there needs to be.
I think the genericity assumption here needs to be adjusted, because the point is that this inner vertex is not generic with respect to the other pinned vertices, right? It sits in the field extension of their coordinates.
Yeah. Something like that will. Yeah, I think that's needed.
Yeah. So I mean, maybe I should have just expressed it that way, but I did look at their paper earlier today to check, and I thought I could say it exactly the way they did, which was this strong condition that the pins can be almost anything. So I'm just bringing their paper to see if I've misquoted something.
They might define generic funny, because that would seem the most logical thing what Will said, to say that PI is generic with respect to the pinned vertices, the field generated by the rationals and the coordinates of the pinned vertices.
Yeah, yes. But they do say for all placements of the pinned vertices with at least 2 distinct locations and all generic positions of the inner vertices. So I think I have quoted it correctly.
Yeah, maybe it's the definition of generic.
I'm wondering whether we should dwell on it or we should move on.
I mean, if we take Will's solution, we're fine.
I think we should just move on.
So probably just move on.
Okay. So the vertices I have a pinned framework are in generic position in their paper if any submatrix of the rigidity matrix is 0, only if it's identically equal to 0 if the coordinates of the inner vertices as variables.
Okay, so this is like the weaker generic of kind of like completely regular sort of thing.
Yeah.
Okay, yeah, but that would fix it then. That would fix it. So this is weaker than what Will said, but sufficient, I think. I think that's sufficient.
Yeah, that's cool.
Yes. So it needs a big star by to change from what I said.
Yeah.
Okay. And so before I continue, any more questions about the theorem? Okay. Yes. So I mean, I want to talk about arbitrary dimensions. So for the rest of the, well, there's not much time left actually, but for the rest of the lecture. But in higher dimensions, we can't have a similar theorem because of the double banana kind of examples still prevent us from having a nice understanding of pinned d-rigidity. But we do have the sort of obvious necessary counts that you want the number of edges to be the rank, which is the number of columns, and you want that inequality to be all the way through. The inequalities we had here, if you think about it for long enough, you can write down similar things for, say, 3D. I just haven't bothered to do it. I just want to, and I just need this condition to explain some of the next things. Okay, so a D-Azure graph is a pinned minimally d-rigid graph, which is minimal in a second sense. So as well as minimal in the sense that when you remove an edge, you remove the rigidity, it's also minimal in the sense that there are no proper pinned subgraphs which are themselves rigid. Okay, so I draw some examples in a moment, so maybe I will defer the examples. So to understand the parts of a pinned minimum rigid graph, which are Azure graphs, I'm going to introduce orientations of the graph. So I say a d-directed orientation of a graph. Obviously, we're going to assign directions to all the edges, and the condition is that every inner vertex has out degree exactly d, and every pinned vertex has out degree exactly 0. Okay. So there is this condition allows me to guarantee that a minimally pinned d-rigid graph can be assigned one of these orientations. So there is graph orientation theory that I think several papers prove it, but the earliest one that I'm aware of is Hakimi in the 60s, proves that every graph basically with this condition can be assigned an orientation with this bounded out degree d, or exactly out degree d if you're tight rather than just sparse, at every inner vertex, and out degree 0 elsewhere. Okay, so I mean, but it is worth saying, I think, that this orientation condition is not sufficient to characterize d-rigidity, it just follows from it. So here's an example of that, and I think we showed this example a little bit ago. We have two pinned vertices, a K4 up here, and what you can see is that, say, at this vertex, it's got out degree 2 and in degree 1. This one has out degree 2, yeah, out degree 2, out degree 2, and then these only have in degree that is not 0, the out degree is 0. So this is an example of my out degree 2, in degree 0. Sorry, out degree 2, inner, out degree 0 pinned orientation of a graph, but it's not a nice rigid one. You can see for yourself that this thing will move. The whole K4 can move as a rigid block, but it will be a non-trivial motion for a pinned framework. Okay, so given one of these d-directed orientations, then you can think about, in any directed graph, you can think about strongly connected components. So here we're going to decompose our graph into its strongly connected components, except there's a little bit of the oddity of including the pinned vertices. So what we do for this is to identify the pinned vertices. So for example, it's maybe not a good one to do here, but the K4 is a strongly connected component, and then you include the outgoing edges coming down from the component, and you include those and sort of collapse everything down and then you would find a second component lower down, perhaps. Again, I think there's an example hopefully coming up quite soon.
Right.
Was there a question?
Oh, sorry, Tony. What does strongly connected mean?
Oh, it means that between any two vertices there is a directed path.
Okay, directed path. Great.
So between A and B, there's a directed path from A to B and one from B to A as well. So you could imagine like maybe a directed cycle is a nice example where this is true. So obviously in a graph like this one, there's only one strongly connected component, but you could imagine that maybe you had two of these cycles. I'm forgetting about pinned and inner just for this picture about the orientation condition. So here you've got a strongly connected component here and a strongly connected component here, and then there's parts that are not involved in them. In general, what we're going to do is form a partial order from the strongly connected components when we're using the pinned vertices and we're using edges down from a component to the lower part. And this partial order we're going to get in this way, which maybe will become clearer when I do some examples, is going to model the decomposition of your graph into its de-Azure subgraphs, so into the doubly minimally rigid parts of it. So we're going to decompose G into components, each of which is a de-Azure graph. And in that context, what you do is that your first one is, of course, it's a pinned minimally rigid thing, so it has to be attached to some pinned vertices. But the second one might only be attached to inner vertices. So the inner vertices in the first component are reinterpreted as pinned vertices to think about the second component. So maybe I'm going to skip ahead and do an example now and then go back up. So here's an example that hopefully makes some of this clearer. So we're in 2 dimensions. I have made 4 pinned vertices and 6 inner vertices. And so and in fact, I'm telling you that this thing is a pinned minimally too rigid graph or framework generically. So for my first rigid thing, what is it? Well, if I just take this vertex and its edges downwards to these 2 pinned vertices, it's a degree 2. So it's clearly a little rigid thing on its own. So in this case, the Azure graph is just, I call it C1, is just this single vertex and its edges down to the 2 pins. And in terms of a strongly connected components, I'm thinking of this vertex as sort of on its own. It's 2 out edges down. It has no outgoing edges anywhere else in the graph, so it can't be involved in any bigger strongly connected component than just itself as a single vertex. So it's a trivial component in that context. And then I can move on and I can look at the second component. And again, it's just a degree 2. I'm going to call it the component C2, and it's 2 out edges down. This one was to an inner vertex, but for C2, C1 is reinterpreted as a pinned vertex, and its other edge down to this guy. And again, the edges were all directed out from it. And then for my third component, I can take, again, it's a trivial component. I take C3, and it's 2 out edges. And then for the last component, where I actually have a non-trivial thing going on, I can look here and say, well, here's a strongly connected component in the graph. This is just a directed cycle, so it's clear I can move between any 2 vertices by a directed path. And it's 3 out edges, the one to a pin, and then 2 of them to vertices reinterpreted as pins to get my 4th component in the decomposition. So I end up with this. In this case, it was I had C1, and then I had C2, and then I had C3, and then I had C4. So it was a very linear order, but in general, it could have been a partial order. Just from degree 2s, you can kind of see that, because it could have been that, say I had another degree 2 that looked like that one. So then at the stage where I got to C2, I could have chosen to go to C3 prime instead. And then it wouldn't have mattered whether I added C3 or C3 dash first. Either one of these could have gone first. And so you can see there's some choice in what you're doing.
C1 has the 2 pin vertices, right? Or is it just the red vertex?
So it depends on how you think of it. I like to think of it as just the vertex here, and then the pinned vertices aren't part of the component, because in a moment we're going to talk about the rigidity matrix, and that's the natural thing there. But it's really a DSU graph is a minimally pinned rigid thing. So in that context, yes, it has to include the 2 pins. It has to be this whole blob. So we're sort of thinking of it in both different ways at the same kind of time. And so
Yeah.
if we think about it in that way, then for C2, you think of this entire thing. So every vertex in C1 is pinned, and then your C2 is like that. And then again, you think of everything in there as pinned, and then your C3 is like that, and so on through the whole thing. And so you do include all the pinned vertices. But if you like, and in terms of the strongly connected components and the rigidity matrix, you think of individual subparts of just parts of the inner vertices as being partitioned into the component. So you kind of have to keep both of them in your head at the same time.
Okay, thank you.
Hey, Tony.
Hi.
So then the decomposition corresponds to one path in that partial order.
Yes, any path through the partial order from the whatever it is, source to the sink or whatever, it is gives you a decomposition. Yes.
Okay.
Maybe I didn't understand the definition of a Azure graph, but is it not supposed to have no pinned minimally rigid subgraphs? But this thing seems to have pinned minimally rigid subgraphs. I got that wrong.
It shouldn't have any pinned minimally rigid subgraphs. So did I make a mistake?
I mean, this yellow, the green graph and the yellow graph seem to. So the bits that you've circled, they all seem to be minimally rigid, right?
Right. So this one was my first one, and that definitely has no minimally rigid subgraphs that are pinned. Then my second one was to do this.
Okay, right. Okay, I get it.
So in the second one, I forget that this is an inner vertex. I forget the edges exist, and this is just now a pinned vertex. And so this thing is minimal. I mean, I was including this before because it's really attached to the whole thing, and that's minimal.
So
and
this
then
is
I go
your so this is the Azure decomposition. You're decomposing any minimally rigid graph into Azure components in this way.
Yes.
Okay, yeah, I misunderstood. Sorry. All right, thank you.
Okay, so I have been jumping around a bit, so I'm probably not being sufficiently clear. So let's go back up here. So what had we said? We talked about as Alex's question, the partial order will give us an Azure decomposition, but it might not be a unique Azure decomposition. There may be different orders you can take things in, say. One thing I want to be clear about, so I didn't go through it in the example, but in the example, I had drawn arrows on the edges and used this to find the strongly connected component that was a directed cycle here. The choice of directions doesn't matter. So I said it has to satisfy whatever it is, this D-directed orientation condition. So it has to be that the out degrees are exactly D for inner vertices, and it has to be the out degrees are exactly 0 for pinned vertices. But that's the only condition. In fact, what's true is that if you take any directed cycle in your graph, in your directed graph, and you reverse the orientations on that cycle, you will not change the strongly connected components, and hence what we're about to see is the strongly connected components tell us the Azure decomposition, and hence if you choose any D-directed orientation, you're fine. You pick one however you like, and it will always work out. That you don't end up having different decompositions into Azure components based on different orientations. It's all the same, so that shouldn't be a worry. Okay, so here's the theorem, which again today I decided not to prove, so maybe I'm just being a bit lazy today. But the theorem due to Offershai, Adnan Shloka, and Walter Whiteley says if you have a pinned minimally D-rigid graph with any orientation of the edges, any D-directed orientation, then the following three things are equivalent. So at this D Azure decomposition, so at the minimally pinned minimally d-rigid subgraphs decomposition. The decomposition into strongly connected components, but we also have a, which I've sort of omitted to say, a block decomposition of the rigidity matrix. So we know we have, let's say we're in D dimensions, we've got DI columns, we know we need to have a square submatrix with DI dash rows for it to be minimally rigid. So we end up decomposing block by block like this. Maybe there should be some dots. And then these things are equivalent. And so the one nice thing about this is that, about the theorem, is that when I'm talking in D dimensions, yet there's this nice combinatorial understanding of the rigid parts of the graph. And the trick, I guess, for that is that we're assuming minimally D-rigid. So we're assuming we don't have problems. We don't have double banana kind of things because we're minimally D-rigid. So the rows are all nicely independent. We know the rank. We know that if as soon as we have something of the right rank, it will be a pinned minimally D-rigid thing, and hence it will be an Azure component in this decomposition. So maybe that sort of gives you a hint as to how at least one of the parts of the proof goes. And again, the strongly connected components are related to this graph orientation thing, which is for the graphs with the sort of D,0 sparse graphs. Any of those can have it, but for D,0 tight graphs, again, you get to these relevant components from your conditions. I appreciate I'm basically out of time, so I'm sort of starting to rush. And maybe I should actually stop because there's probably too much to fit into 1 minute. So maybe I will stop, and but I'm happy to answer any more questions, and I can, if people want, in the next lecture I give say a bit more about Azure decompositions. I did have a few more little remarks and a result or two to mention.
So will you be in the next lecture discussing applications of this?
I forgot, to be honest. What was I going to say? Yeah, so I was really going to do very little, as you can see, more. The sort of the main thing is that strongly connected components can be tested very efficiently. So if I give you a minimally D-rigid pinned graph, then you can tell me very efficiently the strongly connected components. And the nice thing about that is if we go to the example that's sort of been destroyed by now. So let's go to it. Let's write out so we start with something trivial, just to build up some space, and then we can maybe have some of the more complicated parts. So if I give you something that's minimally pinned D-rigid, then what I think what the engineers like about Azure graphs is that it says, well, if I delete one edge somewhere, which vertices move in the, so what parts of the mechanism they've created are actually moving nicely. And so it should be clear from the minimality of the things, if there's no rigid subgraph at all and you remove something, that everything will move. So if you're in an Azure graph and you remove an edge, they call it a driver, which says that everything goes into motion. Whereas if I remove one up here, then clearly the things down here are not going to move. And so they can control by looking at which part of the decomposition is what's in motion and what's not. So I think that's kind of the intuition for the kind of applications they're interested in.
Okay, and I guess you can apply this to Lemang graphs by just pinning two vertices or pinning an edge effectively, I guess.
What do you mean apply it to Lemang graphs?
So, I mean, if I wanted to see what happens to the Lemang graph, like how it moves when I remove an edge, like what parts of the graph move, all I need to do is take my Lemang graph, pin both sides of an edge and delete that edge, and then just do the Azure decomposition of the pinned framework, I guess. And then that would tell me what happens when I remove certain edges and stuff.
Yeah, I think so. But there's a related problem that's a bit subtle though about Lemang graphs. So somehow looking at these Azure graphs for pinned is easier than the Lemang case. So if I give you I might get this wrong because I haven't thought about this for quite a while now, but given a minimally rigid in the plane graph whose only rigid subgraphs are, let's say, single edges, I want to give this a name. So a minimally rigid graph whose only rigid subgraphs are single edges is called I'm going to say MIG. So this is just consistent with a paper of Rudy Penner from the 90s, I think. So here's what I think is a hard problem. Give a Henneberg, recursive construction of MIGs.
And you want every step to be a MIG?
Yes, yes. Well, if you didn't want that, then just the one that exists for Lemang graphs would work.
Yeah.
And so this to me is a sort of analogous kind of situation. So minimally too rigid, but the only rigid subgraphs are single edges is somehow a mysterious class of graphs that would have interesting applications. And if you like this where I said single edges, you might replace that with are complete. So you might allow a triangle. You might say triangle is fine, but nothing bigger. But in either case, I think there'd be interesting applications if this could be done. But I think it seems, well, at least to me, it's hard. And so I'm a bit, in general, a bit concerned about moving to Azure-like things in the non-pinned world because of this kind of problem.
Okay.
It doesn't say what you said was false. I think what you said was true, but I'm just saying there's some subtleties around the unpinned world with this kind of problem.
Maybe it's fine because the Azure decomposition is not going to give you a one extension, a Henneberg recursive function. It's different to that, I guess. Yeah,
I guess I just like the opportunity to advertise this problem that I'd like to solve, but haven't managed to for quite a while.
It sounds interesting.
Yeah.
Okay. It might be more tractable in 2-2 tight graphs, actually. But I guess that's a completely different problem.
Why? I never thought of it. Maybe. What's the analogous question for 2-2? Are you talking about the red question or the black question? Or the in-between one where triangles are okay and K4's not?
Yeah, so kind of my idea would be that you can't have, you probably don't have like the vertex to K4 extension move. Maybe. I would need to think about it, but I think maybe you wouldn't have something. Oh no, you could still possibly have that. Okay, no, forget what I said. Actually, I'm not. I go back on what I said. It might still be very difficult.
I'm writing it down because I have no idea why it would be interesting, but just because I like 2-2 tight graphs, so it might be interesting to me.
Okay.
So the problem with and where I'm keeping people longer than maybe I should, but so the problem, I guess what you're saying, Sean, is that if you had a 2-2 tight variant, you might get rid of the problem where you try and do a recursive construction of 2-2 tight graphs, where you have lots of K4s in your graph, and now the degree free here can't be reduced because it's in a K4, but maybe all of them are in K4, so maybe your graph looks something like this one. And now nothing's reducible because they're all in, there's no degree 2s and all the 3s are in K4s, which you don't want, and you want to be in the simple graph world.
Yeah.
So if you said the only rigid subgraphs are single edges, then this graph would disappear. But even in the 2-free world, I have no idea how to do a reduction at a degree-free vertex, because it might be that there is a large set here with 2x minus 4, which I'd be perfectly happy adding the edge in and still being 2-free tight. But now I'm not, because it would create a 2-free tight proper subgraph, and hence it wouldn't be in this no rigid subgraph case anymore.
Yeah.
So the blocks to the degree-free moves are much more global than K4s. So in either case, the 2-2 tight world or the 2-free tight world, you'd still have this sort of worry.